Alright boys, welcome back. Welcome back to OpenGL. We are hitting episode 40 now. It's crazy. But it's been a good journey, and we're going to be doing something pretty cool today. And just a fair warning, this may be the point, or this has been the point for me where I'm going to have to start extremely evaluating performance, because on my laptop where I tested this, I was noticing frame drops. I probably won't see it on here on my desktop just because of the GPU, but it's gonna start having to, that's gonna be a larger factor now that I take into consideration when looking at code. What's up, Chris? Alright. But yeah, so that'll be something that may pop up a few times. We have been looking at some performance issues, but not too much, but it'll be more of an element for consideration now. But anyway, today we're going to be looking at the point shadows, so point lights. Last time we did the spotlights and their shadows, which was pretty similar to a directional light. Alright, you're here for the discussion. Nice. Yeah, I'm pretty much going to be following this, the Learn OpenGL stuff, mainly for the concepts, once again. But integrating it with our current kind of engine will be a little interesting, to say the least. So, yeah, point lights. The difference between point lights and directional lights or spotlights is that with the point light, you have light emitting in all directions. With directional light, you only had a single direction, therefore you could use an orthographic projection. With spotlights, you could kind of bound the angle of the cutoff angle, and that would allow you to keep it on one plane. However, now that we have light going in 360 degrees in 3 dimensions, we're gonna have to use something different. We can't just, one 2D plane will not be enough. So we're gonna have to use a cube map, which we have looked at before, and we're just gonna be, we won't be rendering it as a cube. So the vertices that we have in our cube map, which are over here, we will not be worrying about any of these vertices, because we're only gonna be caring about the textures, and we're gonna be rendering the depth map onto the textures of the cube map. So essentially this will be kind of like where we did skyboxes with the cube map. It's going to be something similar to that, where we're rendering onto a texture, but the thing is, the object will not be the cube, it will be the rest of the objects in the scene. So we're going to have to, what this entails is, now that we have a separate face for, I'm going to pull something up real quick. Where is it? Yeah, so something like this, where we're going to have each kind of square, each face in the cube map will correspond to some direction, where the point light is the center of the rendering. So we're going to be rendering everything from the point light's point of view, but there's no real way to do 360-degree rendering, so therefore we're gonna have to kind of have different matrices to render. So if you can think of each of these each of these squares is going to be one depth map in that certain direction. So that this will be positive x, then we'll have a negative x, then we'll have positive y, and positive z, negative z. So now that we have 6 kind of depth maps here, we're going to have 6 view matrices, and one for each direction. And this will be pretty simple to implement. We can kind of just look at the code that we have over for the spotlights. Over here, it's going to be pretty similar. We're going to have the projection matrix will stay the same, because it's still going to be the same perspective view. However, we're going to have 6 view matrices because the direction is going to be the thing that's changing from face to face. So we're going to have 6 of these view matrices, and they will each correspond to one of the directions. Okay, so we will start with the code now, and we'll start in cubemap.h because we, like I said before, we did cube maps before with skyboxes, and this was we wrote this code to render as a cube, as an object, and that had preloaded textures. But now because we have a depth map, the data is not going to be, we can't load the data in upon initialization, so we have to have an allocation method like we do for the other textures. So we can just add a simple method in cubemap.h, and we can just call it void allocate, and it'll have the same parameters as the texture allocate. So it's glenum format, gluint width, gluint height, and glenum type. And then we'll also have another method to bind, so just void bind, and then a get method for the ID. Or we could move this ID into the public domain, just to make things a little simpler. Yeah, because we have this with the texture, so why not? Alright, so we gotta go into cubemap.cpp now, and we'll define these methods. So for allocate, the process is going to be a combination of the texture allocation and the cube map texture loading, because we're going to have to initialize 6 texture slots, or 6 texture memory slots. But the difference is we won't be loading in actual images, we're just going to be allocating memory like we do with the texture allocate method. So the signature, make sure to have your cube class tag or cube map class tag. And then here, we're gonna have we're gonna set the variable has textures to true. That's just a variable that doesn't really matter in our case, but we're just gonna set it to true because we're rendering textures here. And this is just a variable that we had for the skybox. And then we're gonna generate the texture, so glgen textures 1, and then a reference to ID, and glbind texture. The type will be glTexture cube map, and then ID will be the texture ID. Then we're going to load in each of the 6 faces. So for unsigned, int I is equal to 0, I is less than 6, I++. And then in the loop, we're just going to allocate the memory. glText image 2D. The target will be glTexture cube map positive x plus I. So this is something that is directly paralleling this here. When we loaded the textures from files, we said cube map positive x plus I. So it goes positive x, positive y, then positive c, negative c. So we're gonna have to set the view matrices according to those indices, where 0 is positive x and 5 is negative z. So this is the target, and then we're going to have the level is 0, internal format we pass in as a parameter, so format, then width and height are parameters of the method, the border is 0, format is format, type will be type, that's another parameter, and then pixels is null, because we are just allocating the memory. Alright, and then before we do anything else, we still have to set our parameters, and you can just go ahead and copy the parameters that we load from the load textures method, because we're going to be using the exact same linear for the minify and magnification filters, and then clamp to edge for the wrap in S, T, and R. Yep, so that's the allocation. pretty straightforward. Then we're done with the cubemap, so it's all ready to go. However, we need to integrate this into our standard shadow format that we have, which is in the FBO. So in framememory.hpp, we have to go into the frame buffer object and actually add a field for the cubemap. So we need to include that. Include cubemap.h, and this will just be another field in the frame buffer object class. Cubemap. Ooh, I did forget to do something in cubemap.cpp. We didn't write the cubemap bind method. I completely forgot that. Just referring to my notes here, just because if I skip one thing, the entire process is just going to be screwed. So let me get. Yeah, bind will just be one line. It's going to be GL bind texture, GL texture cubemap as a target, same as above, and then ID for the texture. And then we can actually call bind in render, but this isn't necessary because it's the same code. Just like that. Alright, in frame memory, I believe we have to add one method. Let me just make sure of this. Yeah, so it's one method, and we're going to call it, it's going to be return type void, and it's allocate and attach cubemap. And we'll have GL attach type, GL format, and GL type. So these are the same parameters as allocating and attaching a texture, because it's still just allocating and attaching a texture, except it's a different type of texture. So we need to initialize the cubemap here. So cubemap is equal to cubemap. This is unnecessary because it's already initialized with the constructor by default. But if we were to allocate this as a new cubemap, we just want to reset the cubemap here. Then cubemap.allocates. We're going to pass in the format. The width and height will be the width and the height of the frame buffer, and then the type will be the type as the parameter here. And then GL frame buffer texture. Note how we're not saying texture 2D because it's a cubemap here. So GL frame buffer. The attached type is just attached type. Then cubemap.id for the texture ID, and then 0. It doesn't like this. Did I misspell it? I did misspell it. Alright. Yeah, so that's a pretty simple method. It's pretty much the same as allocating and attaching a texture, except more of the work is being done in the cubemap class. And actually, this is bothering me that the format isn't the same here. So I'm going to go into cubemap and I'm going to kind of make the form or the template more like the texture class, where we have a generate method that is separate. So just void generate, and then bind is width is just below that. Yeah. Everything we've written so far is correct. This is just one thing that I just want to make more uniform. And all generate will do is just call glgen textures 1 and then a reference to ID. And this is in the cubemap class. And then we can call these methods within the cubemap class, both in load textures and then allocate. Or actually, we should not call generate or bind in either of those. That should be done separately. So in frame memory, or in the constructor of cubemap, I want to call generate. And then in framememory.hpp, before we allocate, I want to say cubemap.bind. So now this kind of allocation is more similar to the texture here. Yeah, so that makes more sense now. Alright, so that's framememory.hpp. And now we're going to go into the light class. And this is going to be the fun stuff. Alright, we'll start in the header file here. And the first thing that I wanted to do was create default constructors for all three of the lights, just because if we have a vector of these, or an array of the lights, there's no default constructor, so that it would produce an error. So just to create a default constructor, just to be safe, is pretty simple. Takes in no parameters. And then we can define these in light.cpp once we get there. Alright. Let's go into point light. We're going to add a bunch of things here. So we have our position, we have our attenuation constants, we have our ambient, diffuse, and specular. That's all normal. And then now we're going to have to add some more constants and variables for the rendering. Like the shadow, or like for the spotlight, we're going to have our bounds, which will be the near plane and the far plane. Because once again, we're going to be using a projection matrix here, which has to be bounded in depth values. And now we're going to have our list of view matrices. So this is the array that I was talking about, where each matrix would have, or each face of the cube map would have its own, each face of the cube map would have its own matrix that would render specifically to that face. So it's going to be glm mat4 light space matrices, and we'll have it in an array of size 6. Then the FBO for shadows is just going to be a frame buffer object, shadow FBO. And then we have our constructors. Alright, so the default is there. We need to add the one that actually takes in parameters. Point lights, this will have taken a position, 3D vector position, float K0, K1, and K2. Then the lighting values, 4D vectors, ambient, diffuse, and specular. And then float near plane and float far plane. And then for the render method, we have to put the extra parameter in there that takes in the unsigned int texture index, like we have for the spotlight and the directional light, because it has to render to some texture slot in the GPU. And then we'll also have our update matrices method. And then now, this was something that I gave a little bit of thought to, not too much, but the way in update matrices, what we're essentially going to be doing is we're going to be if you take a look at the spotlight update matrices, we're going to be doing this, the exact same thing, except we're going to have 6 different light view matrices. And we'll have 6 direction vectors and 6 up vectors. Now I was thinking about the best way to store this, and if I made it a local variable to the method, that would have to be initialized every time. But if I made it a variable of the structure, it would be present for every light. So I just decided, why not make it a static variable? So it would be shared amongst all instances of the structure. So that was just the way I thought about that. So we'll have a list of directions. This is going to be a static glm vec3 directions, and it's going to be an array of 6 of them, and then list of up vectors too. Static glm vec3 up, or you can just call it UPS. This is not paid promotion by the United Postal Service. This is just ups, because I call it directions, so ups. You can call it up vectors, it doesn't matter. But I just need to get it out there. This is not sponsored. Alright. Alright, now in light.cpp, let's start with the default constructors, just to get those out of the way. Just copy and paste all the definitions here. And then we'll just have empty bodies. Alright, let's start now with the point light code in light.cpp, and we can just go through the constructor first. You can go ahead and copy the signature just so we don't have to type out all of the parameters again. But we do have to type out the initializer list that will just initialize each of the values to the parameters. Position, going to position, constants, go to themselves. The lighting values go to themselves. The rendering bounds go to themselves. And then for the FBO, we can initialize that here too. So shadow FBO will initialize it with a width of 2048, height of 2048, and then the only bit that we'll use is GL depth buffer bit. Now in the body, we want to generate the FBO, so shadow FBO.generate. It does not like this. Oh, I didn't put the tag for the constructor. And then standard to everything else, we're going to have shadow FBO.bind, shadow FBO.disable color buffer, and then shadow FBO.allocate and attach cubemap this time, GL depth attachment, GL depth component, and then the type will be GL float. And then update matrices. Alright, for shader, or for render rather, make sure to add that extra parameter in there, just the unsigned int texture IDX. And then we're only gonna have to render, or put in 2 new uniform values. Just you could set the near and far planes, but we won't need the near plane, you only need the far one. to set near and far planes. So shader.setFloat name plus dot far plane in quotations, and just pass in far plane. You know what, just set the near plane just for uniformity. And then the texture. And this is going to be pretty much identical to this, except we're going to have a texture bind call. So GL active texture, GL texture 0 plus texture IDX. OpenGL doesn't give a shit if it's a cubemap or a 2D texture, it's still a texture. So it occupies a texture slot, texture ID. So you just call active texture. And then shadow fpo.cubemap.bind. Then shader.setInt name plus dot depth buffer in quotations. And then texture IDX. Yeah, so this is stuff we've seen so far. Alright, now for update matrices, this is going to be mainly similar to the spotlight, just with an extra loop in there, just to render all 6 of the matrices. So update light space matrices, void point light : update matrices. We're going to calculate our projection matrix because once again that is the same for each of the faces. So GLM mat4 proj is equal to GLM perspective, and we're going to pass in the FOV, so GLM radians, and it's going to be 90.0 float on the dot, because since we have, I mean, if you have this is a little weird to explain, but it's just going to be 90, because how do I want to say this? I mean, you kind of just, it kind of makes sense, because if you think about making a cube out of 3D triangles, and you kind of take a slice down the middle of the cube, the triangles that you get will have a right angle at the center. So that's going to become our field of view, essentially. That's honestly the best way I can kind of say it. But yeah, so it's always going to be 90. So this is our FOV. Then the float value for the shadow, FEO.height, divided by the float value of the shadow, FEO.width for the aspect ratio. And then near plane and far plane. Now, as for the view matrices, we're going to say we're just going to go through our loop for unsigned int I is equal to 0, I is less than 6, I plus plus, and then we'll say light space matrices at I is equal to projection times GLM look at the position, the center of our view should be position plus, position plus point light, the static array, point light, : directions at I, and then point light UPS at I. And we will define these right now. So this is just what we did with the spotlight, multiplying the projection by the view matrix, which we get from the look at, just doing it 6 times, once for each face. Alright, so now let's do the static arrays here. So we can do that above the default constructor here. Alright, so for static variables, you just have to put the type, GLM vec3, then the class tag, so point light, : the name directions, and then have the 6 as the array size. And then you don't have to have the static keyword in there, this just defines it automatically. And then for each direction, we're going to set, once again, it's positive x first. So 1.0 x, 0.0 y, 0.0 z. Then for negative x, it's going to be negative 1.0, 0, 0. Then for positive y, it's going to be 0.0, 1.0, 0.0. Then negative y, 0.0, negative 1.0, 0.0. And then positive z, 0, 0, 1. And then negative z is 0, 0, negative 1. Yeah, that's a little bit of a bitch to type out. Alright. And then we'll do something similar for the up vectors. List of up vectors, and the only requirement here is that it just has to be perpendicular to the direction vector. So you could these are just arbitrary choices. You could pretty much do anything here. So we'll just have the same kind of name here. So glm vec3 point light : ups size of 6, and this is going to be equal to our array initializer list here. And I'm just I can use an initializer list to initialize the vectors because the glm vectors are just a structure, so you can just put them in curly braces, and then we'll interpret it as x, y, and z. So for positive x, we'll have an up vector of 0, negative 1, 0. Then for negative x, we'll have the same 1. Once again, these are pretty much arbitrary choices. I just got them from the Learn OpenGL site just so I didn't screw anything up. I mean, I could probably test with it to avoid any plagiarism issues, but that won't arise. But these are just choices, but they just must be perpendicular to the direction vector. Then 0.0, 0.01 for the positive y. 0.0, 0.0, negative 1.0 for negative y. Then 0, negative 1 for positive z, 0. And then 0, negative 1 for negative z, and then 0 again. All right. All right, so I believe that is it for the... Yeah, that looks about right for light.cpp. Once again, we're just taking the corresponding direction vector, and it is necessary that this order is kept because the texture values that we set, where is it? In cubemap, where we go positive x plus I, this order goes positive x, positive y, positive z, negative z. So it is essential that these direction vectors directly correspond to that. So the first one is positive x, then negative x, then positive y, and so on. Alright, so we're done in the light classes, or the light structures. Now we can go to the scene class, and we'll have our traditional method of rendering the scene, or rendering a shader for the specific light type. So scene.h, we'll have set the uniform shader variables for now the point light render. So it'll be void render point light shader, pass in a shader, and an unsigned int idx for the light index. And we can copy and paste this into scene.cpp for a definition. Make make sure to add your scene class tag. Oops. Now this is going to be a little weird, a little different from the other two, because once again we have to have 6 matrices, but then we're also going to need to determine, we're going to have to pass in a few other variables so that we can render it to the proper face. So the first line is shader.activate. Then we'll set our light space matrices. So this is going to be, instead of 1 call, we'll have 6 calls. So for unsigned int I is equal to 0, I is less than 6, I plus plus. Then shader.set mat4 light space matrices, this is in quotations, and then open square brackets. Then close the quotations plus std to string. We're just going to be converting the integer to a string, and then plus, and then in another set of quotations, the closing square brackets. And then the matrix will be point light at idx dot light space matrices at I. So the idx is the index of the light, I is the index of the matrix within that light. And then 2 more variables here. We'll have the light position. So shader.set3float light position, and then point lights at idx.position. And then we'll do something similar for the far plane. Shader.setFloat far plane is the name, and then point lights at idx dot far plane. Okay, and then before we leave the scene class, we have to go into render shader, and we have to pass in the texture index to point lights at I.render, and we can just do that the same as we have for the other 2 lights. It's just going to be texture idx minus minus. Alright. Yeah. So this is once again in render shader. Alright, so I'm going to say a few things before actually writing the shader code about how the shaders are going to work. We never did anything about geometry shaders before. We haven't, but today we are going to use them. And the general thing that you need to know is that they come in between the vertex shader and the fragment shader. It's a completely optional step. You don't need to actually compile anything with the geometry shader. But in the geometry shader, you can pass in custom vertices based on the vertex shader into the fragment shader. So in this, I linked this article down below. Essentially the code here says, every time we call emit vertex, it will take the value of GL position and pass it into the fragment shader, and it will set the color accordingly. So we call emit vertex twice here, and then end primitive, so OpenGL knows that we finished with the shape, with the polygon, with the line, with the point, with whatever, and it can end, or it can move on to the next primitive. So we could have how many ever vertices that we wanted here. I could build everything in a geometry shader. Technically, if I wanted to do so, I could pass in positions of the cube into the shader, and then I could take care of all the vertices, the -1, -1, -1, and I could do that in here and just call emit vertex, and it wouldn't really matter. I could do that if I wanted to. But once again, this is an optional step, so we haven't needed to look at it yet. But we will today, just because it will make more intuitive sense on how we are rendering to each face of the cube map here. Just because you can't render, you could do this in two ways. You could either render the scene 6 times, or you could do 6 passes from the geometry shader. It really depends. But we're just going to do the geometry shader method just because it seems a little more intuitive. So we're going to have a completely new set of shaders. So we can leave the shadow.vs and shadow.fs as they are. We're just going to create new files. So let me... Oops. Alright, we're going to create 3 new files here. Touch. Point shadow.vs. Point shadow.gs. And point shadow.fs. Oops. Alright, we'll start in the vertex shader here. So same header, hashtag version 330 core. Then we're going to take in our traditional layout variables, just only 3 this time. Layout location is equal to 0 in vec3a pose. Layout location is equal to 3 in vec3a offsets. And layout location is equal to 4 in vec3a size. We're going to have no uniform variables. We're just going to have one void main method here. And what this will do is it will do the model transformation. So gl underscore position is equal to the vec4 of a size times a pose plus a offset. And then 1.0 for the 4th element. The reason why we're not doing the matrix multiplication here is because we can't emit 6 vertices from the vertex shader. That can only be done through the geometry shader. So we pass in the world space coordinates of the lamp of the vertex, and then in the geometry shader we're going to translate it to the lights, or to the specific projection and view of that specified face, of each face rather. And in the geometry shader we're going to have the same header, hashtag version 330 core. We're going to have layouts, and this code I have directly ripped off of learnopengl.com. I should probably put a comment in here, just so I don't run into anything by mistake. So let me go ahead and find the link to this. Oh, not that. Here we go. Here we go. No more plagiarism, boys. Taken from Learn OpenGL by Joey DeVries. I'm going to make sure I spell this name correctly. Alright, yeah. Perfect. Okay. So in the geometry shader we can have the same layout variables, except it's going to be different syntax here. So layout triangles in parentheses in. Let me just make sure I have the right code here. Yep, that's just a layout variable, and then we can also specify the output variable here. Layout triangle underscore strip, and then the second value in there will be max underscore vertices is equal to 18, and that's going to be out. So this is going to be an output layout variable, something we have not seen yet, and the reason why it is 18 is because we're going to have 6 triangles. So 6 faces is equal to 6 triangles is equal to 18 vertices. Now we're going to have our uniform for our uniform matrices. So uniform mat for light space matrices, and it's going to be an array of size 6 here. And then the out vec4 frag pose. And then void main. We're going to have a loop here, so for int face is equal to 0, face is less than 6, face plus plus. Then we're going to use a OpenGL's built-in variable to determine the face on the cube map, and this is specific to a cube map. So GL underscore layer is capitalized, is equal to face here. And then we want to render the triangle. So for int I is equal to 0, I is less than 3, I plus plus. We're going to get the current vertex, so frag pose is equal to GL underscore in at I dot GL position. So this is now, this might be starting to come together for some of you. When we say layout triangles in, what that means is we are taking in full triangles. So we pass through the vertex shader 3 times for each shape, and then we want to take each vertex separately, and then say get the position, so GL, and then now we want to transform it, so GL underscore position is equal to light space matrices at face times frag pose. So this is where we're actually doing the transformation. In the vertex shader, we didn't have an output variable for the frag pose like we usually do. We're doing that here. This is our output variable. This output means that it's going to the fragment shader. So we get the GL position from each vertex, and this setting it to frag pose is almost as if we were taking it from the vertex shader, which we are. It's just indirectly, or not under the same name. So we're getting the GL position, which we set right here, and then we set the GL position of the variable of the vertex to pass into the fragment shader and transform it to the light space, and then we're going to emit vertex in the loop. So emit each vertex separately, and then after that inner for loop we're going to end the primitive and then render it on the next face and the next one. Yeah, so that's the geometry shader. Pretty intuitive when you think about it. I'm gonna fill up my water. I'll just leave this up here. Alright, now onto the last step of the shader process, which is the fragment shader. Fragment shader, same header, hashtag version 330 core. We're going to take in a vec4 frag pose, which comes from the geometry shader for each call to emit vertex, And then here we also have our two other uniform variables, uniform vec3 light pose and uniform float far plane. So the shader is going to be a little different than what we have for shadow.fs, where it was just empty, because we're actually going to be customizing the depth value ourselves here. So void main, we're going to get the distance between the fragment and the light position here. So float light dist is equal to the length of frag pose dot xyz and minus light pose. And then we want to map this value to 0, 1 just by dividing it by the far plane. So light dist divided by equals far plane, and then we're going to write to the depth map. So write to depth map, and we can do this by saying gl underscore frag depth is equal to light dist. And the reason why this writes to the depth map is because we attach the cubemap as the depth attachment. So when OpenGL renders to the cubemap, it will look for whatever GL frag depth is, which is automatically set, but we're just customizing it here. And this just simplifies the code in the object fragment shader. I will also look at doing something similar in the other shadows, in the shadow.fs, just to make it more consistent. But yeah, that will be something we do next time, I think. But yeah, in this one, I just wanted to get the concepts and the code down, just so we have something. And then next time we'll do improvements and optimizations, like we did with the original shadows. All right, now that we have our 3 shaders, it is not enough because our current shader only supports a vertex and a fragment shader, so we need to add a way to pass in a third path for a geometry shader. So in shader.h, all we have to do is just add a new parameter to the constructor and the generate functions. So it's another const char star geo shader path this time, and by default it will equal null pointer because it is optional. Generate using vertex frag and optional geometry shaders. Alright. And then in shader.cpp, you can go ahead and just add those paths here. And then make sure to pass the GeoShader path into generate in the constructor. And then for the generate, add the parameter. Or const char star. And then in shader.cpp in the generate method, this is going to be really ugly the way we write this, but we're going to have 3 checks to the whether or not GeoShader has a value, because everything is done sequentially. We can't compile the shader, attach it, and then delete it before doing anything else. I mean, technically we could, but it would look awful. So we're just going to do it in 3 different checks. So gl uint geoshader is equal to 0. This is just going to be our placeholder. And then if geoshader path, and this works because geoshader path is a pointer, so if it's null pointer, this returns false. Then we say geoshader is equal to compile shader, and we're going to pass in the file path as geoshader, and GL geometry shader is the path. And we wrote this compile shader method a long ass time ago. Ooh, yeah, pass in GeoShader path to that. And then after we attach the fragment shader, we just do another if statement. So if GeoShader path, or we could just say if GeoShader at this point, because otherwise it's going to be 0, so that will be false. So if GeoShader, either one works. Then GL attach shader ID and GeoShader, and then the deletion at the end. So if GeoShader, or you know, just make a GeoShader path just to be consistent. GL delete shader GeoShader. Yeah, just make all 3 if statements say if GeoShader path just to make it consistent. Alright, so now the shader class is ready to handle another shader type, or another shader type, the geometry shader, which is cool. Now under the second page of notes, this is a long, I had to write a whole dissertation just to get this prepared. Yeah, the rest of this stuff is mainly mock-up. Once we do the object fragment shader, everything else is going to be mock-up and just preparation. But this is the last kind of algorithm part to it. Alright, let's go into object.fs. And we will start in the point light structure. So we need to add our 2 new uniform variables, float far plane, and then for the map, we're going to say sampler cube, not sampler 2D, because it's a cube map now, depth buffer. Or, yeah, depth buffer. And then in the main loop, I'm going to go ahead and disable the spotlight results and the directional light results, just so we can look at the point lights initially, and then we'll add the others after. So it should only be result plus equals the calc point light for each of the point lights, and the calc dir light and calc spotlights are both commented out. Alright, now as we did for the other ones, we're going to have a separate method to calculate the shadow for the point lights. So it's going to be returns float, calc point light shadow, pass in an integer IDX for the light index, then a vec3 norm and a vec3 light direction. First we're going to get the vector from the light to the fragment. So vec3 light to frag is equal to the frag pose minus point lights at idx.position. So this should immediately be reminding you of this right here in the point shadow.fs, where we calculated the difference between the two. So we're getting that vector, and it turns out that this vector is actually the coordinate of the point in the cube map, because cube maps have 3D coordinates, and it's a little weird to think about, but the cube map is a 3D texture in all. So we're going to have each float value between, or each we have a fixed just think about layers of think about it as you know, the cubes that you played with in elementary school, and how you kind of got what 3D was in a way, where you started out with the line that was your 1D, then you put those together like you had a line of 10 cubes. Come on, I need to find an image of this. Yeah, these things. You had like a line of them, or I remember differently, but it was something like this. So you start with a line, so let's say you start with the red, then you make a square, which is the whole thing. That's your 2D plane. And then, so that's our texture, that's our 2D image that we have for the other depth buffers. And now we're just essentially stacking those up to make a 3D cube map here. You guys have to know what I'm talking about with this. It's like a Rubik's Cube, but with a lot more, where each cube is a pixel, kinda. But yeah, this is what I'm talking about. 1,000 cubes, 10 cubed, 10 by 10 by 10, stuff like that. Alright, yeah, so this is the coordinate, and just like the shader does with the other textures, it takes the float value and puts it into the pixel coordinates that the cube map will understand. And then we're going to get the depth from the cube map. So float closest depth is equal to texture, and then the texture will be point lights at idx dot depth buffer, and the coordinate will just be light to frag, and then we're going to get just the red value from this from the texture, the pixel value. And once again, it knows that this is a cube map because we bind it as a cube map, so it knows it's taking a 3D coordinate. And then in the fragment shader, we mapped the distance to 0, 1, just so it would actually render as a usable color, because you can only have 0 to 1 in the texture. So now we're just going to get it back to the regular depth. So 0, 1 to the original depth value. So closest depth times equals point lights at idx dot far plane. And then we're going to get the current depth. And how do you do that? Well, we don't have any projection matrices here, but we have the distance from the point light to the fragment position. And this is why the cube map is pretty cool here, because we're looking in 3D space. We're not confined to a 2D depth buffer anymore. We're looking at 3D space. So it's just going to be float current depth is equal to the length of the light to frag. And then the one optimization that we will do here will just be the bias, just so we don't see that striped bullshit. So calculate bias, float min bias, god damn it. Float min bias is equal to 0.005, float max bias is equal to 0.05, and the bias value is equal to the maximum of max bias times 1.0 minus the dot product of the normal and the light direction, and then close those parentheses, and then min bias will be the other parameter. For the reasoning behind this, watch the video where we improved the shadows. I think it was around 40, so episode 38. And then, like with the other ones, we're going to say return current depth is greater than, or current depth minus bias is greater than closest depth, question mark 1.0, colon 0.0. We're leaving out the PCF for now, because that's just I don't want to worry about that, just because it's a little extra, but we will do that next time. Alright, and then in the calc point light, we need to call this method. So before we return the vec4, we're just going to get the float shadow value is equal to calc point light shadow. We're passing in the index, the norm, and the light direction. And then we'll just take the shadow, do 1.0 minus that, and multiply that value by the diffuse plus specular. So it should be return the 4D vector of ambient plus, then in parentheses, 1.0 minus shadow close parentheses, times, and in another set of parentheses, diffuse plus specular, and then close parentheses twice. Alright, that is all of the algorithm stuff, actually. The rest of, we're just going to be formatting some other classes so that it actually works, and then we'll integrate it with the main file. So we need to go into cube.hpp now, and since we have one method to render the entire scene, and that takes in only one shader, we can only now void the lamp fragment shader where it takes in a light color, and we have to actually replace that with a material. Don't worry too much about this. It's just if you don't have a render scene method, then you don't need to worry about this. But just because we pass in one shader to this, we have to have it formatted like the rest of the objects, where we take in either a material or a texture value. So in the cube class, we'll have a material value. So material M, and then we can just initialize this in the text in the constructor. So material M as a parameter will be equal to, by default, material : red plastic, and then just initialize it in the list. So M goes to M. And then in init, where we set the static variables as the colors, just replace it with M. So where we say material.redplastic.diffuse, just change that to M.diffuse and M.specular.R.G.B for all 6 of those. All right. Oops. Yeah. Oh, M.diffuse. And then in lamp.hpp, we just want to pass in, we can just pass in white rubber as the material here. So material : white _ rubber. Alright, now into the main file. This is where the magic happens. This is where you go to Disneyland and get disappointed by your $18 popcorn and hot dog. Alright. First thing we're going to do is we're going to create our shader to actually render the shadows for the point light, because they're different files. So we can actually delete these here. And also delete the lamp shader, because we don't need that anymore. So shader, point shadow shader, and we're going to pass in 3 values here: assets / shaders / shadows. Just do the paths to the vertex fragment, the vertex, then the fragment, then the geometry shader. So shadows / point shadow.vs. And then .fs for the fragment shader, and then .gs for the geometry shader. So that's our point shadow shader. And then we want to reinitialize our lamp value, or our lamp model, and make it a global variable so we can access it in the render scene or in the render scene method. So just move its initialization to above the main method, and it still should register normally. And then we can go ahead and uncomment all the stuff about the point lights. So everything here that we have for the point lights is commented currently. We can just go ahead and uncomment it. And then everything looks good except for the constructor, which we will do in a second. Or let's just do that now. So the point lights array, when we initialize each element in the array, we now need to call the constructor because it's explicit. And you can pass in the point light positions K0, K1, K2, ambient, diffuse, and specular. And then for the near and far planes, we just need 0.5f and 50.0 float. And then for the spotlight, I'm just gonna save or comment out the activation of it, just so because I don't want to render it right now. Okay. Alright, let's go into render scene now, where we have to render the lamp, or add the rendering of the lamp. So scene.render instances, lamp.id, shader is the shader and DT, standard stuff. And then now in the main loop, what we're going to do is what we have been doing. Like the spotlight, we're going to go through each lamp. So we're going to say render scene to point light FBOs. So for unsigned int I is equal to 0, I is less, or len is equal to scene dot point lights dot size, I is less than len I plus plus. And if states dot is index active, a reference to scene dot active spotlights or point lights, and the index is I. Then we're going to say scene dot spot dot point lights at I dot shadow FBO dot activate. This is just stuff that we've done with the spotlights here. And then scene dot render point light shader. The shader will be point shadow shader, the new one that we have, and then I for the index. And then render scene point shadow shader. Just rendering the scene from the shader. And once again, when we call this, it will render everything from the point light's point of view, which means it goes through the model transformation first to put it in world coordinates, then goes to the geometry shader, and it's transformed 6 times to get to each face, and then each one of those triangles, so each of the 6 triangles is then emitted as a vertex and then passed to the fragment shader to be colored customly to the depth buffer. Alright, and then the last thing I wanted to do was we can just actually deactivate or cancel the rendering of the spotlight, and then I just wanted to change the position of one of the lamps so that it was overhead so you could see the shadows more. So I'll make it one of the lights 0 15 and then 0. Alright, you boys ready? You ready to make sure you get your diapers on? Uh-oh. It's just gonna blow my computer up. There's no... I swear to God, if this tanks the frame rate, I'm gonna be pissed. Fuck. No, god damn it. Oh, yeah, okay. I know what this is. I'm getting errors about the scene because in the cubemap, because there was declaration issues, circular definitions. So all you gotta do is, if you get this error, you can do the forward declaration of the scene class in the cubemap class. So in cubemap.h, just replace the include of the scene file with class scene and end it with the semicolon. No curly braces, because we have a pointer here, so it doesn't care how much memory it is, it just cares how much memory the pointer is, which is 4 bytes. And then in the cubemap.cpp class, or file, we then have to include the scene class, so that the definitions are included. So include /scene.h. And the reason why we needed this was because in the render method, we called scene methods here, right over here. All right, now let's run this. Come on. God, this is edging me. Come on. Fuck. What is... What? What's wrong? What? I'm confused. What does this mean? Alright, let's just try running it again. God, fuck. This is similar to the fucking hackers getting hold of the CVT cock prisons, and this is just, I'm being edged so much right now. Holy fuck! Hopefully no ransomware pops up and be like, I will free your cock if you give me $15,000. But come on, this error is just so. All right, what happens before cubemap generate? Ooh, you know what it might be? Okay, I think I know what it is. Because we call generate by default in the frame buffer class, so we should not call generate in the cubemap constructor, and we should just call it directly in allocate and attach cubemap here. So in framememory.hpp, in allocate and attach cubemap. After calling the constructor, we should say cubemap.generate. I don't know, maybe that caused it. I hope it did. And come on. Well, alright, let's go. Yeah, the boy. Oh, fuck. There's nothing. 657 megabytes. Oh, this is no bueno. There's nothing. Alright, that is definitely a fragment shader problem. Object.fs. Let me just try making it black to see if... Okay. So it's the... Ooh, that's a lot of cubes, holy shit. Okay, so it's the point lights calculation. Calc point light shadow. Alright. This was compiling properly. What's up, Solomon? It compiled. It was compiled properly. Just I'm not enjoying this. Maybe let me try removing the shadow calculations, or just making shadow is equal to 0.0, just to see. Huh. Then it has some... Let me try... Return vec4 0.0. Okay. So I don't think it's an issue with the shadow. It's then an issue with some of these values. Oh, Lord. Okay, let's, did we come... Alright, let me make sure render shader is applying the proper point lights here. So I'll put a breakpoint there. Point light size is 4. Active point light's 15. That looks right. Yep. Alright, then it is likely this. We didn't change anything. God, fuck. We didn't change anything in pointlight.render except we just added 2 things. We didn't remove anything. Let me try removing these calls here. Nope. Just continue. What the hell? This is so weird. Because even if this returns 0, the main method should be... What the heck? Alright, let me say this here. What the fuck? I'm beyond confused here. Oh, number of spotlights, not number of spotlights, number of point lights. I'm just testing here. Okay, alright. So it's getting the point lights. Let me alright. The only explanation here is that it's getting a negative value for the 4th component, but that doesn't make any sense. I mean, I could try doing vec3, just converting this to a 3D vector and then converting it back to a 4D vector, just to ensure that last component is actually 1. Ooh. Maybe. Nope. Holy shit. This is baffling. What is... Oh my god. Let me try removing the gamma shit here. That might be it, but I don't know why it would be. Nope, it's not the gamma. Or the depth testing. Why? Alright, it has to be calc point light. Let me go through calc point light once again. Alright, got the ambient, point lights at IDX. I don't know why I'm going through this, because this all works. Specular, 0001. But, then this has to be that some values aren't being... Return vec4 0.0. Okay. So for some reason we're getting a negative value for the fourth component, which doesn't make any sense because I tried to remove it, but Alright, let me try doing this here. Return vec4 ambient plus diffuse plus specular. Alright, it's... Okay, then this has to be a uniform issue then. Alright, that makes more sense because these calculations look correct. Position, ambient, diffuse, specular, K0, K1, K2, far plane, sampler, cube, depth buffer. That is right. And there aren't any new variables, new uniform variables that have been changed. Alright, let's go to light.cpp, see what's happening. Oh, you know, I did not uncomment these, so maybe it was that, but still don't see it being that. Alright, so that's good. Makes no sense. Alright, light.cpp. Let's see what values we set here. Point lights at, or point lights plus standard 2-string IDX, name plus dot position. K0, K1, K2, ambient, diffuse, specular, near plane, far plane, then GL active texture plus texture IDX, cubemap dot bind, this is making no sense. This has to be a uniform issue because even if I commented out the shadows, the shadow calculation, I mean, fuck. Maybe I just say return 0.0, so it's never in the shadow. Oh, what the fuck is this? What is it? These lights look super jank. Okay, that doesn't, I mean, it's there. Okay, so. Alright, so it has to be this then. Because then it's getting some error over here that's not allowing it to do anything. Okay, this makes more sense now. Alright, object.fs calc point light shadow. This is where the error is. Alright, light to frag is equal to frag pose, capital F, capital P, minus point lights at idx, which is a parameter dot position, which is a member of the structure. Closest depth is equal to texture, point lights at idx dot depth buffer, light to frag dot r. Could be this. Could very well be this. Closest depth times equals point lights at idx dot far plane. Then we get the current depth, which is the length. 1.0 minus. Let me try setting it to the closest depth, or just return the closest depth to see if that makes a difference. Because I'm feeling like it could be this, if it's just not reading anything. I feel like that could be the problem. You know, but no, even if it wasn't reading anything from the texture, it would just return a 0. Oh wait, I say return 0 here. Return closest depth. Now let's return this. Okay, yeah, okay. Closest depth is the thing that's not working. It's breaking something. Okay, point lights at index dot depth buffer. Let me make sure that this is the right name. Point lights depth buffer. Let me just minimize these so it's easier to go through. Alright, so it doesn't like that this value isn't being set. Or it's just not, it has an error with texture values. Alright, let's go to scene.cpp. Render texture index. Name plus. Just not seeing this being the problem because this is all. So bind texture is GL texture cubemap ID. So let me see if ID actually gives anything. ID is 130. That's a non-zero value. That looks good. All right, let me go here. Alright, GL gen textures. Yep, GL gen textures. Good. 1 and then a reference to ID. Cubemap.bind. GL bind texture, GL cubemap, ID, good. Then allocate. Hash textures is true. Sure. And then I from 0 to 6. Text image 2D. Okay, it's still text image 2D, that's fine. Yeah, it's GL text image 2D. Positive x plus I. I is 0, good. Fuck. Depth attachment, depth component, float. God damn it. This is looking all right. Not sure what this issue could be. Let me try this here. Cubemap.id is 130, that's good. I'm considering just restarting this album. This is too quiet. This is... Oh, man. Alright, so it is not figuring out what this is. Maybe I'm gonna try normalizing this. The light to frag. For the position at least. That could be it, but I don't think that would change anything. Nope. Son of a bitch. Everything else was the exact same as it has been. I don't know why this is it's looking at it differently. It might be that it's a cube map, but I don't see why that would be any different. Because we've done cube maps before. Do I still have the shader? Oh, there we go, skybox. Texture. Yeah, vec3 text chords, uniform, sampler, cube, skybox. That was something else. If this goes on for much longer, I might just call it. The exact same code is written in my reference and it worked. It has to be something with the cubemap. I don't see why it would be any different. The only thing that I guess I did different was I just created the methods for the generate and bind, but I let me try doing that in here. GLGen textures. If this works, I'm going to be kind of angry. Alright, thank God. So it's not that. It has to be some memory thing. Like, there's really nothing else that I could think of. I mean, just gonna try changing the parameters. I doubt this isn't not gonna do anything else either. Yep. Let me see what GL text image 3D is. No, that doesn't look right. No. I mean, I could try something here and say return point lights at idx.depth buffer is equal to 0, question mark, if it is equal to 0, return a 0.0, otherwise return a 1.0 for the shadow. I mean, I could texture size. I could try calling this, see what it does. Alright, yeah, this has to be some uniform dumb bullshit. Alright, I'm wasting my time just looking at this. This is not productive, so I'm gonna end the stream here. I will grind my ass off into oblivion to figure this out. And video will be posted fixing this. Once again, I don't have the slightest clue. I know it has to do with the texture, but that's all. Like, I hope I'll figure it out at some point, and then yeah, I'll post a video once it's fixed, along with a video detailing the improvements and the PCS stuff like that, and then we'll be moving on from shadows after that. I think we'll be doing some more lighting stuff, which will be cool. But yeah, point light shadows. I hope this code works on your computer, because this exact same code is working on my laptop. And if it is, give yourself a round of applause. Go jack off into the sink as a celebratory, just as a celebration, and then maybe I'll get to that point. Maybe. Let's hope I do. But anyway, I hope you guys enjoyed. Hope you learned something, and I will get back on the issue whenever I figure out what it is. So I will. I'll see you then. Take care of yourselves.